All right, let's take a look at an example of something that we would use mathematical induction to prove. So we're going to let n be any natural number, prove that 1 plus 2 plus 3 all the way up to n is going to be equal to n times n plus 1 divided by 2. Now, this type of proof, you might have seen other creative ways of doing it, which is perfectly fine. Also, you may have seen this statement look a little bit different. If you think back to Calculus 1 and we looked at things like sigma notation, what we're saying is that we're saying the sum from I equals 1 to n of I is equal to n times n plus 1 divided by 2. So these two statements are saying the same thing. So we'd like to prove that this is going to be true for any natural number. So what my proof is going to look like, so I'll do proof by induction. Again, we said the first thing you need to start out with is the base case. So we're going to have this base case. We're going to say let n be equal to the smallest value that it's going to take on. And so since we're just working with the natural numbers, the smallest value n will be is 1. So let n be equal to 1. Now what's going to happen is we're going to look at the left-hand side of this and the right-hand side and see, do those equal each other? So we see 1, that's the left-hand side. This is equal to 1 times 1 plus 1 divided by 2. So 1 is equal to plugging in the same thing, n equals 1 over there. Done. Base case. Base case should be usually very easy. If it's not very easy, probably made a mistake somewhere. Or it's just a really hard question. But I don't know if we'll see those. All right, now we're going to do the induction hypothesis. Induction, actually I'm going to call this the induction step. So my induction step is going to contain both the first assumption, which is the hypothesis, and then try to show that if it's true for n, it's true for n plus 1. So we will assume that 1 plus 2 plus up to n is equal to n times n plus 1 divided by 2 is true for n. Then we'll prove this is true for n plus 1. Okay, now this is where the meaty part of the proof comes in, is what does this mean and how do we do it? So I'm assuming that basically for the variable n, this is going to be true. If you look up other proofs and other strategies, you might see people say that this is true for n equals k, prove that it's true for n equals k plus 1. I don't really like adding in an extra variable unless we really need to. But if what I'm doing is going to be really confusing and you're using another resource, feel free to do that if you need to. Okay, so what I'd like to do is basically I'm going to work with one side and show that by manipulating that side, I am going to be able to get to the other side. Okay, so what this means is I'm going to work with this and I'm going to include n plus 1. So we'll prove this is true for n plus 1. So we see 1 plus 2 plus 3 plus n plus n plus 1. What is this equal to? This is not equal to n plus 1 times n plus 2 divided by 2. We cannot make that assumption, right? That's what we're trying to prove, so don't assume that's true. So I'm just working with this. This is equal to n plus 1, or this is true to n times n plus 1 divided by 2 plus n plus 1 by the induction hypothesis. So by the induction hypothesis, we know that this is true. Why? Well, because 1 plus 2 plus 3 all the way up to n, we said that that was equal to n times n plus 1 divided by 2. We assumed that this was true. Now we're trying to manipulate this to be able to get to our desired conclusion as though you plugged in n plus 1 into this expression. So now notice here that n times n plus 1 divided by 2 plus n plus 1. I could factor out an n plus 1 if you want. You could find common denominators. There's lots of ways to go from here. So I have n times n plus 1 divided by 2 plus 2 times n plus 1 divided by 2. So I'll do common denominators here. I can factor out an n plus 1. They both have over 2. Factor out the n plus 1, and I'm left with an n plus 1. And then what I'm left with then is an n plus 2. So now I've shown that 1 plus 2 plus 3 all the way up to n plus 1 is equal to n plus 1 times n plus 2, which is equal to 2. And if we look back at this statement, if you think about plugging in n plus 1 here, you would have n plus 1. N plus 1 plus 1 would be the same as n plus 2 over 2. So you've shown that this statement is true for n plus 1. So notice we have this, hence, our statement is true for n plus 1. So by induction, this statement is true for all n in the natural numbers. So we wanted to prove that it's true for all n of the natural numbers. We showed the base case was true. We showed this inductive step was true by using the induction hypothesis. And then we have our desired conclusion, because by induction, that just takes care of all of the heavy lifting to say that that is true for all natural numbers n.